Hello, welcome to another Stat 510 video. In this video, we're just going to very briefly talk about decision theory. We're going to I'm going to outline some of the main concepts real quick, but basically the only reason I want to talk about this is so we can get to one one of the most interesting result in statistics at the end of this video. None of this information will be tested on the final, but I want you to have this information. There's going to be one homework question where you explore this very interesting result. Okay, so if you think about what we've done in this class, really it boils down to there are parameters, theta, and we want to estimate them with estimators, theta hat. That's a lot of what we've done. And we've seen various ways to come up with these estimators. We've seen maximum likelihood. We've seen method of moments. Just last video, we introduced this notion of using Bayesian statistics to come up with a posterior distribution and taking the mean, and that will get you a point estimate. Great. But the question becomes, well, how do we pick between these things? Like, which one is best? And the field of study within statistics that looks at this kind of question is something called decision theory. A brief note, in academia, there's this thing that happens where different subfields, different fields, they have to go and rename everything. But so what we've been calling estimators, sometimes someone that studies decision theory, they'll call it a decision rule, but it's an estimator. That's confusing. Anyway, so I'm going to overview the very basics here. And again, this is not going to appear on the final. There's just going to be one homework question or two homework questions, one in particular that's very interesting. So the first thing you need to ask yourself is, well, how do we quantify the difference between the value we get through our estimator with the true value of the parameter? And obviously, in practice, you just can't do this because you don't know the value of the parameter. But when you're studying statistics academically, you can control the situation and simulate from some model with a particular parameter value, and we could do these sorts of calculations or simulations. So we often talk about loss functions. So losses are different ways to measure the difference between the true value and the estimated value. So the first one here, which I've starred, is the very most common. It's called squared error loss. It looks at the squared distance between these two things. But there are many other loss functions you can consider. Absolute loss is another popular one. I would note that for computational reasons, historically squared error loss is more popular, but absolute loss is certainly valid and actually has some very nice properties. Estimators that have a small absolute loss. This is tangentially related to quantile regression, which is something near and dear to us here at Illinois. Another example here is 0-1 loss. This is something that might come up a lot in sort of like classification methods where you just care about if you categorize something right, and if it's right, you get a 0. If it's wrong, you get a 1, and so on and so forth. And all sorts of other loss functions could be considered, but we'll largely consider squared error loss here. But just know that like right away, that's one way the complexity of this could explode, is there's all sorts of different loss functions you consider. But what you quickly realize is that, well, this is clearly not going to be enough, because this is only going to consider the distance between the true value, which again, we only know in simulated examples that we sort of use to evaluate these methods, and one value of the estimator applied to one data set. But often, that doesn't tell us anything about the method. That just tells us like, oh, this one time it worked out. So what we really care about is the risk of an estimator, which is effectively the expected loss. So you just do exactly that. You take the expected value of the loss function with respect to the population distribution, which depends on that parameter that you're trying to estimate. Because again, you can only do all this stuff if you actually know the underlying distributions. Now, it turns out that we've already seen the risk for a lot of these estimators, because under squared error loss, what this boils down to is the mean squared error, which we have previously seen is the variance plus the bias squared. So we've been looking at this. We just haven't used this loss and risk nomenclature to talk about it, but we've already been doing this for all intents and purposes. Okay, cool. So now often So something you might not realize yet here, but I think I'll make it clear in a couple slides here, is that this risk is in some ways a function of theta. So because in practice we wouldn't know theta ahead of time, oftentimes we want to consider the risk for all potential values of theta. But then then we want to like work backwards and get a one number summary. So two ways to do that are either the maximum risk or the Bayes risk. So the maximum risk says, okay, the maximum risk is the worst possible risk you could have by essentially picking the worst possible value of theta to be estimating. So you would want an estimator that minimizes this maximum potential risk. And when you achieve one of these estimators, that's called a minimax estimator. Now, we're not going to go into the theory of deriving minimax estimators. It's very difficult. This is way beyond my ability level, but that is something that you could seek to do. Alternatively, we could look at the Bayes risks. Now, to do this, you have to specify a prior over the parameter value that you're interested in, and then essentially it averages over that. So maximum risk only considers the worst case scenario, whereas Bayes risk sort of averages over all possible scenarios. And the estimator that minimizes the Bayes risk is called the Bayes rule. And again, we're not going to go into deriving all these things, but in the reading, there's a lot more depth here, but I'm just trying to introduce the very basic concepts. So a real quick example. So let's say we have a random sample that's IID Bernoulli, and we want to consider two estimators for the parameter P. The first is the usual MLE, just the proportion of times these random variables come back 1. The other is that thing we derived last time, which is going to be the posterior mean if we had a beta prior. And we want to ask the question, okay, well, what is the risk of using these two estimators with squared error loss? So recalling that the risk under squared error loss is just the mean squared error, we very quickly can get those two risks. Now, the risk for, this should say 1, and this should say 2. So now, note that the risk of the second estimator depends on the prior that we chose. So arbitrarily, for reasons that are explained in the book, I'm going to choose a prior with both alpha and beta equal to square root of n over 4. That is arbitrary for all intents and purposes. There's a little bit of explanation of why that is in the book. But when we do that, we end up with this risk here. And something that might be interesting to note is that when doing this, the risk of the first estimator actually depends on the true value of p. So for different p's, we're going to get different risks. Whereas the second one is actually constant, which is nice. And there's some theory when you get that, but I'm not going to dive into that. It's in the book if you're interested. But so what I want to do then is, so here is a plot. So for different values of p, the second one is always the same. Whereas for the first one, it's different depending on the value of p. And we can see right away that the maximum risk is going to be here on this one and here on this one. So the maximum risk of the posterior mean is lower. So in some sense, we like that. I think that's what we're going to see right here, right? So we can do this calculation, and it turns out that the maximum risk is smaller for the posterior mean. So you could say, okay, so that's the better estimator. But we could also look at the Bayes risk. And if we did that with just a simple uniform prior, so not sort of making any sort of crazy judgments here, we would end up with something that looks like this. So in this case, for large enough n, the first risk, the first estimator, the usual MLE, has a lower Bayes risk. But so basically, long story short, is this picture is more informative, but often we like a one number summary. But basically, the first estimator is better when you have sort of large or small p. The second estimator is sort of generally better when you have a p closer to 1/2. And that again is because the way this estimator works, this p2 hat here, is kind of biasing the results towards certain values. And that has advantageous properties if the true value p is close to those things. Okay. Right. So one more quick definition and then an interesting result. Okay. So a lot of times what we really want to avoid is using a bad estimator. And a bad estimator is one that is basically uniformly beaten by another estimator. So if we go back here, like there's neither of these estimators is always better than the other one, right? So they're both valid in some sense. But so what we're defining here is this notion of if there is some estimator and we need a prime here and a prime here, else this doesn't make sense. So suppose we have some estimator theta hat, and then there's some other estimator theta hat prime. If for every theta, like the true value, the risk for theta hat prime is less than or equal to the risk for theta hat, and for at least one value it's actually lower, then we say theta hat is inadmissible, because theta hat prime, it's either the same risk as theta hat or lower. So why would you ever use theta hat? Because this other estimator is just uniformly better. It's not a situation like this where sometimes one is better, sometimes another is better. It's just, no, there's this theta hat prime that's always better. So yeah. So if there doesn't exist something like that, we say theta hat is admissible. Proving things about this is, it's a whole difficult thing, but we're not going to get into that. So what we're going to do now is talk about a very interesting result. This result is called Stein's paradox. So suppose we have a vector theta of a bunch of parameters, theta 1, theta 2, all the way through theta k. And what we're going to observe is a vector x that contains x1, x2 through xk, where each individual x is sampled from a normal distribution with the corresponding theta as the mean. So we could call this the many means problem. And for the sake of simplicity, we're just going to assume they all have standard deviation 1. You could have different variances or some non-1 variance, but we're not going to talk about that case. So now what we're going to do is define a loss. So ultimately, we want to estimate this theta. So we're going to kind of have this summed squared error loss, right? So compare the estimate for each theta to the true value, difference them, square them, sum them. Okay, so there are two estimators that we're going to consider. One is the MLE. So if you only have one observation corresponding to each theta, well, then the obvious thing to do is just use that value as the estimate of theta, right? Because, normally you'd use x bar, but with one observation, the observation itself is x bar, so that is the MLE. Now, we're also going to introduce this new estimator. It's going to be called the James-Stein estimator, named after statisticians James and Stein. Stein is, I think we've mentioned him previously in the class because we've previously mentioned University of Illinois professors Portnoy, who was Stein's student out at Stanford in years past. So there's some lineage there. Right. So what is the James-Stein estimator? So what it does is to estimate each of the individual thetas, it takes the xi that was sampled from that normal distribution with that theta, but then it does this other thing here. And if you think about the possibilities here, and so this is borrowing information from all the other values, regardless of whether or not it came from that value of theta or not. But essentially, if you think long and hard about this expression, what this does is, in some cases, nothing. So it would just become 1 and nothing happens. But a lot of the times, what it's going to do, it's going to be a number between 0 and 1. So what it does is effectively it takes the value xi and it shrinks it. So it makes it smaller. In particular, it moves it closer to 0. Now, it turns out, and now, right away, like we can all scream, this is bias. This is a biased estimator, no doubt, right? You're literally biasing the result towards 0. But it turns out that if k is 3 or above here, so when k is 1 and 2, the MLE is perfect. It's admissible, well, not perfect. It's an admissible estimator. But with k 3 or above, it's inadmissible because the James Stein estimate produces a lower risk than the MLE. That is a shocking result if you think about it. So we're just going to arbitrarily, well, not arbitrarily, through this cleverly derived expression here, we're going to purposefully bias our estimates towards 0, and that's better than not doing the bias. So this is a huge result. It's very surprising, and you'll see hints of this other places in statistics, like maybe you've seen shrinkage in the case of regressions, like a lasso or a ridge or something. But this is an idea that's very important to a lot of nonparametrics these days. Very important idea. It's crazy. So again, you'd think you want to just use this MLE here, but it turns out that if you shrink your estimates a little bit, you end up with a lower risk, and the MLE is inadmissible because of that. Perhaps you don't believe me because I'm not writing a proof here, but hopefully after doing the homework where I forced you to do some simulations about this, you will believe this result. Yeah. So that's all I wanted to say about decision theory, mostly to get to this wonderful, interesting, crazy result here. But remember, there's just a couple of homework questions on this, but it will not appear on the final exam. Okay, so as always, if you made it to the end of the video, good job, and I will see you in the next one.